Okay, this section of this module is about database storage concepts. So the first things we got to talk about is the basic structure of how things are sort of put together in a geodatabase or any kind of database, really. And the first thing we want to talk about are fields. Fields have specific types, and they have to be defined before you can use them. And once you define, you can't change them. And there's also rules: no more than 13 characters. You can only start with letters and numbers. Only use letters and numbers, and it has to start with a letter. And so that's what fields are. Fields, if you want to think about this in terms of like an Excel file, would be columns. Now, within a given field, data can be stored in a lot of different ways. And so we're just going to talk very briefly about what some of this means, and we'll go on from there. Binary data is a fundamental mode of how we store things in computers. Data is stored as a series of zeros and ones representing numbers in a base 2-bit system, and so on and so forth. And this is all interesting and clever, but it's not really something that you necessarily need to know per se. ASCII is another file type that we come across pretty often. The American Standard Code for Information Exchange, ASCII 2, or ASCII, depending on how you look at it. It stores letters and characters and symbols as 7-digit binary codes. And from that, it allows you to store complicated data sets like large rasters as simple, basic text. So text data is always stored as ASCIIs. Numerical data could be stored in ASCII or binary. Binaries are generally more efficient than ASCII. So what are the limits? This is where we start to get to the point where it becomes important. I'm not going to be quizzing you, or we're not going to be quizzing you or testing you on your understanding of how the binary system works. What matters is a single byte is a value between 0 and 2 to the 8th minus 1. And what does that mean? Well, what it means is 256. So when we look at large numbers, they require more bytes. So if you're at 255, that's 1 byte. If you're at 65,000, 2 bytes, 16 million, 3 bytes, etc., etc. If you have signed numbers in terms of like positive and negative, requires a little bit more to store positive or negative numbers, so the storage limits are smaller. So instead of 2 bytes being 65,000 and change, it becomes 32,000 and change. Why? Because it has to be 32,000 on the plus side and it has to be 32,000 on the minus side. And so what matters is you understand the limitations in terms of the size of the number, okay? And so if you're looking at basic things like colors, where you're between 0 and or 0 to 256-ish, 1 byte works. If you are going to be somewhere between plus or minus 32,000 and change, 2-bit will work. If you're looking at elevation numbers and you're like 56,000, 2-bit will not work. You have to go up to 3 at least. If you have elevation numbers that have negatives, then you can't go to just a regular 3-bit or something like that. You'd have to go to a signed, which means that then it drops down as far as what you can have, and so it will dictate your choices. Another common choice is integer versus float in terms of storage. Floating point gives you decimals, integers are whole numbers, binary stores whole numbers. To store decimals, you have to switch to the scientific notation and store it as floating point. Now, raster data does not like floating points, so this can create some issues sometimes, and you have to go through some somewhat complicated gymnastics in your table or your toolbox to get attribute tables to attach to rasters that are in decimal format. It's likely you may not come across this, but it is something that you can solve. It just takes a bit of work. Floating precision, large numbers start to lose precision because the number of significant digits in the mantissa is limited. So when you have a really big number, even though you have a lot of decimals, you end up with a bunch of zeros at the end. Or if you go to double precision and floating point, like we mentioned earlier, you have much more digits in the mantissa that allows you to have much more accurate, larger numbers. So when we look at how we store this stuff in databases, they're typically defined as either ASCII or binary. We talk about the bytes of storage that's allowed and whether we're going to be an integer or floating point. The definition limits of the values that can be stored. You want to make sure that the type and the requirements are all sort of lined up and try to minimize storage space while making sure all the potential values fit in the field. And there's a couple of examples. For example, the text field ASCII field, if you use 10 bytes, will only allow you to store that much of the word Mississippi. So you lose an I because of it. Where if you're in a binary 2-bit signed integer, you're only plus or minus 32,000 change in single precision floating point. Again, certain number of decimals in the mantissa. So understanding this will help you set up your databases properly and select the right kind of fields for any features that you're creating. Now, having said all that, this little green box is your best friend. If you can commit this to memory, or better yet, copy it and save it somewhere so that when you need it, it's there, that'll help you out a lot, because then you can know what kind of fields you need to have. If you're looking for like 2-bit binary numbers or ranges of values between plus or minus 32,000, short integer. For bigger numbers, long integer. Decimals, floating point. Really big numbers with lots of significant digits, double. Text, text. Date, date, etc. So you can go through these exercises if you want. I'm just going to pause for a couple seconds on each of these slides and allow you to think about this, and you can sort of answer what you think. What kind of storage should be used for each of the following data type, how many bits are needed for each field. You can look at the previous slide and get some idea about this, and in your learning module you should have access to the slides themselves as well as this video.